Too many microphones. Hey everybody, welcome, CS109. I'm going to do the first part of this lecture and tell you a bit more about MapReduce, especially the combiners. That was not me, was it? Especially the combiners, and then Rahul is going to take over and tell you about Spark. But first of all, I have something serious. Our homework collaboration policy. That's on me. That was me. Do you need to check something? Anyways, slides are not that important at the moment. We might have some technical difficulties. Our homework collaboration policy, if you look at the web page in the syllabus, or you're basically bound by the Harvard Honor Code, right, in this course. And this means the work that you hand in must be your own. We expect that you cite all sources that you use from outside, and we expect you to not share code, right? We have this rule on Piazza, no posting on code, that also does not only account for online collaborations, but of course also in real life. And guys, we're data scientists. It takes me 20 minutes to get a ranking of the similarities of these homeworks, corrected for variable renaming and passages that were very common. So please, just don't let me have to deal with this. We already have a few cases that we have to look into, so please don't make it anymore, right? So, on the more joyous side, fun side, MapReduce. I'm going to repeat a bit from last time to get you into the middle of things again. So we talked about this whole cluster framework called MapReduce. And the idea is that you don't have to deal with all the nitty-gritty details of the cluster, right? You don't have to deal with nodes all of a sudden dying or slowing down, restarting jobs, how many nodes to use in the beginning at all. The MapReduce framework does all of that for you. No free lunch, then on the contrary, you're bound and constrained in what you can program, in what style. And the way to think in this framework is in map and reduce steps. So we already talked about the map and the reduce last time. We had this word count example that I'm going to go briefly over again, because this is where we're going to take off again. The main thing to learn is that everything comes in key value pairs now. And in the beginning, very beginning, we often don't care about the key, but the value. And then the mapper does something with the key value pairs it gets, outputs different key value pairs. Then there's this shuffle and sort phase. And afterwards, I have all the values that have the same key aggregated in a list. And actually, it's not a list, it's an iterator. Some people came down last week and asked me why in the anagram example, there's a line of code where I take this, which already looks like a list, and put it into a list. Sorry, I didn't copy that slide again. That's because this is an iterator that comes out of there. It's not a real list, so you need to reformat it. But just for the concept-wise, you basically have this whole assembly of all the values that belong to one key. After the shuffle and sort phase, the shuffle and sort is transparent to you. You don't need to do anything with this. And in fact, you can't do much with it. So all these things come then out, and then you program the reducer again. So the reduce step, again, is your responsibility. You need to decide what to do now with these values that you get associated with one key, and then you create your final output. And we did talk about this word count example with I like green eggs and ham. And here you had the mapper and the reducer. Let me make a bit more room. And in the mapper, we just went over every word in one line. And then we yield. This means we return an iterator, basically, that goes over all the words. So the output pairs now are the words in lowercase lettering, and the value is just 1. So the magic in a lot of MapReduce programs out there comes in the shuffle and sort phase. That's where all the computations actually take place, because this mapper is pretty dumb, right? Only outputs all the words it has seen and 1. and then the shuffle and sort does the majority of the work, and then the reducer again has an easy job, because now it gets for one word all the ones that were output previously by the mappers, and it just needs to sum them up. That was our basic MapReduce example. Do you have questions about this example? Okay, then let's take off from there and let's see how we can make things more efficient. Because I simplified the model so far. So you really want to avoid communication overhead in almost all of parallel programming. In this case, in MapReduce, you can basically think, I want to generate as few key value pairs as possible, right? Especially in this case, like dumping out a 1 for every word in there is a lot of key value pairs, which means in the shuffle and sort, right, there's a lot going on, because there are all these key value pairs to process. So we need to think about how to reduce this overhead. And the way to do this is called combining. And I actually simplified the model before you. This is the real MapReduce. So you see there's the mapper that we're already familiar with. And here's the reduce that you know about. And here's the shuffle and sort. And because the shuffle and sort is this very expensive part, you can actually try to reduce the workload by using these combiners here. And the partitioners I'm not going to talk about in this lecture, but with these you can basically influence how things are separated for the shuffle and sort. But we're going to just focus on these combiners here. The way to think about a combiner is almost like a mini reducer. The idea is, for example, in our word count, I do not need to see every one out there for this particular word to be able to construct the sum. Would be totally fine if this mapper would already see, I've seen the word house 3 times, and I've seen the word Sam 50 times, right? I do not need Sam 1, Sam 1, Sam 1 50 times. I actually would be equally happy if this mapper says, I've seen Sam 50 times, and this mapper says, I've seen Sam 30 times. Output that as a key value pair. And then in this reduce here, it would get Sam 50, and what did I say? 30? 50, 30, and output 80. Right? I could aggregate the results before the shuffle and sort. And that would reduce the load here a lot. So this is exactly what these combiners do. So the idea of a combiner is basically that it is a mini reducer. It takes the mapper output before shuffle and sort. So it's before shuffle and sort, and the mapper output goes directly there. And the idea is that it significantly reduces network traffic by already computing parts of the results. Important is this combiner does not have any access to other mappers. It will only see the key value pairs that come from its mapper, which means this combiner, right, cannot assume that it's seeing all possible Sam count pairs, right? Because this mapper here also can see lines where Sam was mentioned. So while here in the reducer, it's safe to assume that when that reducer gets Sam and all the values, I know that this key Sam only came out once of the shuffle and sort. You cannot make this assumption in the combiner. It's getting only the key value pairs from this mapper. The other thing to keep in mind is combiners are not guaranteed to run at all. This is the MapReduce framework trying to optimize runtime. If the MapReduce framework notices that this mapper is really fast and this guy is really slow, what it's going to do is when this guy finished already, it can run the combiner, maybe even multiple times. Whereas if this mapper finishes fairly late, it might not run this combiner at all and just start with the shuffle and sort. So the idea is that it's up to the MapReduce framework in the background to optimize how often it will run the combiner. And it might run it multiple times, it might run it not at all. That's the way to think about this when you debug. I said before, when you use the mappers and the reducers, basically in your head, just think about one key value pair. That will do the trick most of the time. With the combiner, the important thing to have in your head is, does my code still run if this combiner does not run at all? Will my code still run if this combiner runs multiple times? Those are two important questions to ask yourself when you program a combiner. So, and this also is, I'm going to answer this question, this is why the key and value output must match the one from the mapper. So if you look at the signature of the combiner, right, it might run not at all. So then this reduce here would get the output from this mapper. Or it might run multiple times, so this reducer, or another one, like the key value pairs are shuffled, output from here might come to the reducer. The reducer only has one signature in the function, which means the output from here, from the combiner, must have the same signature as the output from the mapper. I have examples for that. But first, let's look at the word count, what it looks like with the combiner now. So this is the more efficient version. So we have our mapper. That one didn't change. Gets the key and the line, splits it, and yields word and a 1. That was the same we had before. The reducer also is the same as before. It just takes the word and the occurrences and sums them up. But now we have this combiner in between. So the combiner actually looks exactly like the reducer in this case. And often that is luckily the case, but you have to see whether those criterion about the signatures are still met. So you have here the word and the occurrence, and you basically already sum up some ones that you've seen before the shuffle and sort. So this idea, I've seen Sam 50 times and I've seen Sam 30 times, that is what happens inside this combiner here. Can you see that? So often combiners and reducers have combiners and reducers have to share the same method signature. Everything that comes into the combiner must look the same as the stuff that comes into the reducer. Everything that comes out of the combiner must look the same as the stuff that comes out of the mapper, right? Because you don't know if the combiner is going to run. So this is the main thing. I emphasize this so much because this is where I run into all my errors. So this is really something to keep in mind. And here's an example that I can go through. So this is computing the mean of some numbers. So this method, the mapper here, outputs some key, a string, and an integer r. And now comes this reducer here. And that gets, again, this key and all the numbers associated with it. So these are now integers. And it sums them all up and counts them. So I have the sum and the count here, my variables. And then I go over this whole list. So for every integer I got in the list that I got up here, right, I now sum them all up, and I count how many they are, and I compute the average. I think I have this as the combiner. I have to look myself. So I'm claiming that I can't just make a combiner that looks the exact same as this reducer. Why? Yes?
Because the combining separate averages, you need to know the weighted average.
Yes. Because the mean of means is not the same as the mean of the original numbers, right? This guy might run once, several times, and I have the reducer afterwards again. So let's try and fix that. Here we separate now the sum and the count. So now I'm saying the combiner here actually takes track of the sum and the counts. And it outputs a pair where I have the sum and all the counts, and then I feed those into the reducer, and that then has all the information to actually compute the correct average. Why does that not work?
The mapper doesn't have the same values as your combiner output values?
Yes. The mapper doesn't have the same output values. So here comes out one integer, and here is a pair. It's not the same signature. I don't know if the combiner will run. This code here assumes that the combiner runs exactly one time even. Because if it would run, it would try to run again its own output, it actually couldn't. So now we fixed that all. There, what did I do? There, up there. So now we fixed this by actually fixing the mapper. So that we're now having the mapper output this pair. And this means the signature now matches here. And we're happy and can actually compute the mean. But this is what I mean with debugging and thinking, like all the thinking is what happens if my combiner doesn't run, what happens if my combiner runs once, what happens if it runs multiple times. So, and I'm actually not going to talk about in-mapper combining. I left the slides in, though. There is another method to do combining, which doesn't even use the combiners, but tries to put everything into the mapper. So if you're interested in how to make this maybe even more efficient on the cost of having to wiggle a bit with more details, you're very welcome to look at the slides. And if you want to know more, you can also come to my office hours. But this is the level of MapReduce that you need for homework 4. So I'm going to close with this, and Rahul is going to talk about the secrets of Spark.
Okay. So continuing from where Verena left off, so we've been talking about all these sort of different maps and reduces and so on and so forth. But let me ask the people here a question. Why would we want to do this? We had this really nice paradigm in which we were doing stuff in scikit-learn. There were nice matrices and everything. Why did we switch to sort of doing this, what looks like this rather bizarre way of writing programs? Can anyone hazard an answer? Go ahead. Large amount of data, exactly. In many situations, we have a large amount of data. So that's precisely one of the reasons why we want to do this. But there's also a second reason. How many of you are at the RBF part of homework 4? Or have it finished it or something of that sort? And if you notice in the RBF part, we just did about 3 points in the parameter space. Maybe it was 3 or 4 points in the parameter space. We didn't do more. And each one of those points in the parameter space maybe took 5-10 minutes to run. So if you really wanted to do a really exhaustive grid search on that parameter space, you know, like maybe 10 elements on one grid and 10 elements on the other, maybe even some slightly better algorithm, we're talking about 10 cross 10, 100, and then 100 cross 5 minutes, that's 500 minutes, that's 10 hours. And if you hadn't started your homework like a long time back, you won't finish it by the deadline. That's why we didn't do it on the homework. But when you're doing a real problem, you wouldn't want to do what we did. We just sort of found a model which was like, you know, which I had pre-tested, because I ran this a lot, to be a reasonably good model, and we said, okay, we'll use this model and compare what the results are on this model. But in reality, what we'd want to do is this big like grid search and try and figure out what the best parameters of the problem are. So for this, we want to sort of now sort of get some idea of doing things in kind of parallel so that we don't spend, you know, all this time. And in fact, you can actually see the structure of this by looking at this kind of picture, which is just basically a picture of a bunch of tests of training sets and validation sets over here, and for different values of a two-dimensional parameter space up there. And it's the same data, firstly. It's just a slightly different algorithm, right, because the parameters are slightly different you're putting in. But it's the same data, and you want to run on this again, right, and you want to run in each one of these. So what's the first thing you might do to make this happen? So if you had to do this yourself, you were given the scikit-learn algorithm, and you had to make this happen, what would you do? Well, maybe that's what you'd do, but yeah. Yeah. Okay. Yeah, no problem. Thank you. So, okay, getting back on track. So someone, what might be the first thing you might think of doing? Just try and come up with ideas. Anyone? Go ahead. Right, the first thing would be to run them sequentially and spend a lot of time. But at some point, you might actually realize that if you took the data you had up to then and you saved it to disk, and then you just send the data to like 10 different, to 10 different processes on your computer, you could run 10 different processes and just run the same algorithm on 10 different processes, right? So you could do those processes in parallel, kind of in parallel. It depends upon the number of CPUs your computer had. If your computer had 2 CPUs, you could probably run 2 of them in parallel, and because each one of them waits a little bit, doing nothing from time to time, you could actually schedule in another one. So maybe you could run 4 comfortably. Beyond that, it might get a little bit hard, right? But you could at least save some time by doing this. I mean, in fact, your next optimization might be, you don't save it to disk, right? You just take the memory that you have out there and you just copy it 10 times in memory. So each one is working on its own. That would be your second optimization that you might think of. In fact, if you think about it a little bit, you might even think of a third optimization. You'll say that this is the training set and validation set. I'm never going to touch this. I'm never going to write anything into this. So I don't even care. I'll just let people access the same memory. I'm not going to write into it, so I'm not going to have like, some big core dump or anything of that sort. My program's not going to crash. It's just going to access the same memory, and we're fine. So, step by step in this kind of iterative fashion, you come up with this notion, okay, I can have multiple programs accessing the same part of the memory and do something with it. So, and if you thought about doing it this way, you'd be kind of correct, because these problems like cross-validation and grid search that we're talking about right now, or even bagging on a given data set, right? Just resampling that data set, they're all what I call embarrassingly parallel problems, in the sense that there is a step at the end where you need to put things together, right? I mean, once you do the cross-validation stuff, you're doing the cross-validation stuff for each point in that grid parameter space, but you're also doing it on 5 different folds. So when you're doing it in that particular fashion, you might say, okay, well, I have 2 steps of combination to do. I need to average stuff over the 5 different folds. And then at the end of the day, I need to do a minimization. So there are these 2 kind of reduce steps, if you like, in this whole process. But the rest of it's completely parallel. The data doesn't change. So I can just use the data again and again. And I can do all of these things in kind of parallel. Now, something like boosting, on the other hand, is not so good for this, right? Because boosting, it looks at the results from the past step. So you can't kind of do this thing in a completely parallel fashion. So what you might do is you might use Python's multiprocessing module, and Python's multiprocessing module lets you create multiple processes, multiple threads, if you like, and access the same memory set, and then do this. And this would kind of roughly be presumably your workflow. You'd say, I have this master program, my original program in which I'm doing this classification. That orchestrates some kind of data split for me, which is kind of useful. Then the cross-validation splits are either like, it's a read-only area of memory, or I basically just replicate the memory multiple times because, my memory is cheap. I can just add some more RAM into this computer. I'll create a pool of worker threads, and each one of these worker threads will basically, a part of each pool will be chunked off for each combination of grid parameters. Each worker computes a validation score. Per subpool, I'll compute an average. Another reducer will compute a minimum or maximum over all these averages, right? And boom, at the end of the day, I have the model. I have the correct model, the correct parameters, and I give it back to the master. And I say, master, go and refit on the entire training set. And that's the scheme I use. Okay. How might this look? So this is another example. This goes to Verena's usual word count example. And this is sort of like, the reason I'm bringing this up is because you can do the same thing with word count as you can do with the cross-validation. It's not exactly the same problem, but it's a very analogous problem, in which what you're doing out here is you say, okay, from multiprocessing, you start up a pool, you load a file, you make 8 processes, you chunk up the text so that you can send a certain amount of text to each one of these 8 processes. Basically, you count these tuples in the word comma w sort of fashion. You do the combining and shuffle part that Verena was talking about in between, and then you do this kind of like summing that's going on in the reducer step, which is that term frequency step, and then I sort it, and maybe I make a graph of it or something of that sort. Again, it's the same idea. It's those steps at the end are the non-embarrassingly parallel part, the term frequencies and the term frequencies that sort. And that single count tuples, that pool.map part, is the embarrassingly parallel part. And the shuffle part is the communication part, which you want to minimize as much as possible of between these kind of things. And if you're doing this in multiple steps, there might actually be multiple phases of things that you need to do as well, right? I mean, if you're doing some kind of nested cross-validation, or you're doing something else with these tuples or something of that sort, then you'll have these kind of nested processes. So you might have multiple such steps. You might have a map step, which reduces the data to something, and then the data again needs to be mapped to do something else, and we'll see an example of this, and then you reduce it to something, so you have these various steps. Now, Hadoop, which is what Mr. Job uses, basically does the simplest possible thing that you might want to do. And what it does is that basically it sort of persists the outputs of each one of these like map and reduce steps to disk, and then reads it again from the disk, does the next step, saves it back to disk. Does anybody know why it saves it to disk? What's one of the advantages of doing that? You might have heard this word in an operating systems course if you ever took one, but the basic kind of notion of there is something called a checkpoint. It's basically saying, okay, this step completed by the great will of the Lord, it completed safely. I'm going to save the data before anything goes bad. Because when you have a whole bunch of machines, right, something's going to go bad. I actually once met Rob Pike of Kernighan and Pike at an astronomy conference, and he said that in some of the places in Google, they don't even actually bother fixing some bugs, which are really, really complicated, but they just checkpoint the data and they run it again, basically. Because they have two things happen. Programs are buggy, and machines just die. So you want to sort of like program in a fashion when you have these large data situations where you do things so that you can actually checkpoint stuff. You don't have to start all the way back at the beginning because these are long processes. You want to start somewhere in the middle. And so that's why, this whole MapReduce thing has this kind of like very weird sort of like, I'm going to get things from disk, I'm going to save things from disk, I'm going to read things again, and so on and so forth. But in your cross-validation process, if you wanted to do that, you'd do exactly the same thing. I said, I don't want to do all these cross-validations all the time. I've done 9 out of them, and my program died, and you're going to make me run all 10 of them again? Well, then you save the results of those 9 ones in some fashion, right? Or you save some intermediate spot, and you go on from there. So that's what you would come up with if you wanted to not do this cross-validation again and again and again. So it's exactly what MapReduce and Hadoop do for you. So going back a little bit to cross-validation, you say, okay, we use multiprocessing. In fact, a lot of the folks who wrote scikit-learn wrote a library in Python that's called joblib, which does exactly this for you and gives you a little bit more. It adds you some caching and disk caching, which you need for this kind of thing if things die. And it's easy to use. And if you saw the labs carefully, you might have seen an njobs parameter in doClassify, which actually comes from the njobs parameter in grid search, CV, cross-validation, and the random forest classifier. And this is exactly what they're doing. They're using multiprocessing. They're setting up basically a thread pool. They're sending off all this data to the thread pool. They're optionally letting you save the state of things while they're running in case something dies. And then you can restart and go on and so forth. So again, it's the same idea of what's going on in MapReduce over here. There's this long piece of computation which is parallelizable, but there's a step at the end where you need to combine things. And in between, we want things to do things like be able to persist stuff, cache stuff, and so on and so forth, so that we can make things faster and more resilient. So all this is very nice. But at this point, you might be wondering, nothing in that cross-validation steps have been, we've seen in scikit-learn, any of these looks anything like that MapReduce word count problem, right? I mean, that's an admittedly rather strange way of writing code. The way scikit-learn does it seems to be at some level somewhat more intuitive. So why are we doing this? Why are we doing it in this rather strange fashion? I'll come back to that in a second. So this we could do on one machine, right? Because that was the data set in the homework isn't that big. But now you're talking about petabyte data sets. You're talking about terabyte data sets. You're talking about huge data sets. And if your problem is really, 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 really huge, one machine is not going to cut it because, it's actually cheaper to get lots of machines with less memory than one machine with a huge amount of memory, right? You can just buy yourself a big cluster or rent it on Amazon, essentially. And do your stuff on it. So you don't even have to buy this huge big cluster and all the people that come along with it and the big room with air conditioning and all the stuff. It actually reminds me of the scene in I don't know, how many of you saw Martian? Right. Some of you must have seen Martian, right? So there's a scene where the astronomer guy, he goes into the big cluster room and he attaches his computer to the big cluster and does stuff. I'm like, nobody does that. You just spin up a cluster on Amazon now. basically. But you have a huge problem and you want to solve it. You need a lot of compute. You need a lot of disk. And not half your machines, but a certain fraction of your machines are going to die. Just because disks will fail, somebody will come with a samurai sword and cut one of them. Something will happen, right? So things will happen. So you move it to the cluster. So things fail. And therefore, we use MapReduce, which saves things to disk, has resiliency, and so on and so forth. But the same things which make things very resilient have some problems. If you're writing things to a disk, and you need to come back and you need to compute again on those intermediate results, as many algorithms you do need to, now you've got to pull those results out of disk again. So that's kind of slow. And that's not the best way to handle some of these things. And the problems themselves, I mean, the way you write this kind of MapReduce code is itself a little bit complex, right? So these are the kind of problems you have in this MapReduce framework, basically. You're writing stuff to disk. It gets you resiliency, very good, but it makes things slow. And so people thought, what can they do to speed things up? So in the context of scikit-learn, there's something called ipython.parallel, which is kind of fast and easy to set up. It takes care of the problem of big. It basically lets you run all your cross-validation steps and everything on different machines in a cluster. And if you go look at the documentation for IPython parallel, and earlier in these slides, I referenced a particular URL with Oliver Grizzle's notes. He actually shows you how to do cross-validation on an IPython.parallel cluster, something that might actually be useful for your projects. So keep that in mind. It's fast, it's easy to set up, but the problems with failures hasn't gone away, right? One machine goes down, and boom, you've lost that part of your cross-validation. So you're in trouble again. So it's okay for graduate student descent, right? If you're trying to optimize a problem by having a graduate student do it and has the 5 years to do the PhD, that's okay. You just go and run it again. But if you're trying to create a production system which identifies fraud within the next half an hour, no, that's not going to work. So you've got to fix this. And this is okay if you have internal clusters. It really depends on what you want to do. For a lot of you, for the project, this might be the way to go. If you need this kind of massive parallelization. So that's one thing. The second thing is that you noticed that there was this rather strange way of writing code that Verena was showing us in these MapReduce programs for word count. But if you noticed a little bit carefully, you would have seen that any step of that program does not have any side effects. What do I mean by this? What do I mean by it does not have any side effects? The idea is sort of simple. It says that here's a function. It takes an input, and it gives you an output. Nothing else happens. Nothing else happens. There's not some other variable which has some state, right? If you write a Python program, you say a is equal to 1. And you have a function def f, and it says a is equal to a plus 1. And that can change the variable from outside. But the moment you've done that, you've created a side effect. Something outside, there's some state in the program, that a equal to 1 had a state. That state got updated to 2. So when you write a function which looks like that, you're writing in a paradigm which is what's called an imperative paradigm, where you have this kind of flow, data flow which goes through, but you're not thinking in a very clear way about the state of things. So in other words, if you were to run this function a second time, something else would happen, and it might not even be nice. But if you had a function which took an argument, instead of def a is equal to a plus 1, you said f of x and return x plus 1, then you're just taking an input x, and you're returning an output x plus 1. And this is very, very clearly and cleanly specified. And if I wanted to do it outside in the program, I would say a is equal to f of a, right? Because I would have a start off as 1, and then it would go inside, and I would return 2, and then I would reassign it to the variable a. And now my function f is a kind of cleanish function. It's not messing around with the state of the program at all. It's actually really clean, and it's just taking an input, and it's popping you an output. So, one of the aspects of writing functions in this particular fashion, writing programs in this particular fashion, is that you eliminate any shared state. And a shared state is a dangerous thing in parallel programs because I have like one thread out here which changes some state, and if the other thread depended upon that old state, it would fail. So that's kind of like a dangerous thing. And then the second thing is that data is explicitly, there's a lot more to functional programming than what I'm saying, but there's a particular thing that's useful for us. The second thing is that data is explicitly passed, right? There's no side effects going on. There's nothing weird going on. No other variables are being set. No, no state is being changed. And so you can think about the way these functions work as a kind of graph where you have an input and an output, and the other thing takes the other input takes the output of that and puts it in. So you could actually imagine that what you're doing is you're basically setting up a bunch of things like this, from which some data is flowing, and some other bunch of things is consuming it. But no state is changing, right? So here's some list or some array which comes in. This outputs another array. That array is thrown in over here, and that outputs another array. So this is array number 1, array number 2, array number 3. This array number 2 over here gets sent here, and you get an array number 4 out here. The point is that these are all different lists. And when I have a program which I can represent as a graph like this, I can actually reason about this program very separately from the data that's actually passing through it. I can reason about where I can run these functions. I can say, well, you know what I'm going to do? I'm going to take 2 of these functions. I'm going to run them in one thing. I'm going to take this, and there's some third one over here. I'm going to run these 2 in some other thread. And this I'm going to run on the master, or something like that. So I can reason on how to do this. All I have to do is to orchestrate the flow of data between these things. So this kind of data flow needs to be orchestrated. And so what I'm doing now is how to transport the data from one function to the other. I'm going to leave up to the framework, the map-reduce framework, the Hadoop framework. And I'm just specifying what these functions take in and what these functions take out. So you should be able to see 2 advantages directly to this. The first advantage that should be clear from this particular diagram over here is that when you're passing data in this particular fashion, the orchestration, as we just said, the orchestration can be done outside. I don't have to do it from an inside perspective. The second thing is that if any one of these machines died on me, like this one died, I know exactly how to get back over here because I know what points in the graph I need to go through to come here. I can look at this graph and I can trace it down. And I can say I can come down here and I can run this. So I can actually reconstruct where I was in the program. So this all worked. I saved it to disk, or I did whatever. This all didn't. I said, oh, I need to actually reconstruct that entire part. So I reconstruct that entire part of the program, and once I finish that part of the program, I restart the whole thing and I go on. I, here being the Hadoop framework, you don't have to do it. You just write the programs. But because you've written them in this particular formalism, and you've guaranteed the Hadoop framework that you are not going to do anything weird. You're going to take in an array, and you're going to pop out an array. You have these nice benefits. By the way, that's also why pandas, if you remember, of all of them, most of the functions you have in pandas, they output a new data frame. They have a data frame, and they do something with it, and they output a new data frame. They don't do it on the same data frame unless you explicitly say in place equals true. And so this is what they're trying to be really careful that even if you have a pandas program, you can compose it in this particular fashion, if you like. And we'll see that when we come to Spark, that Spark also does similar things for you. Okay, so therefore you have guarantees on reconstruction when things fail. You know how to reconstruct stuff because you know which part of the graph that you need to go over again. And finally, because all this thing is done by the Hadoop framework, you can have this external orchestration, and therefore you can do the scheduling. As Verena was saying, that you can have, oh, this thing finished fast, I can run the combiners here. This thing didn't finish fast, okay, I won't run a combiner. All this scheduling can be done external. There, of course, you give the program one more guarantee that you had exactly the same signature as well. So you helped it along. Okay, so that's why you need to do this kind of functional programming. And map and reduce are really some of the basic aspects of this functional programming. Map is simply take a list, produce another list from it. Do something, but produce another list from it. Do not return that same list. Do not write in that same list. If you ever write in the same list, the evil lords of functional programming will come and hit you with a stick. You must always return another list. That's critical, okay? Okay, so what do we want? We want something that's resilient, something that has this kind of checkpointing business, so that if things die, you don't have to restart right at the beginning. You want something that's fast, does not always store to disk, and you would think that 2 and 3 are generally not compatible with each other, and you would be right. 2 and 3 are generally not compatible with each other. You want something that's replayable, because you can refigure out which path in the graph you need to take. And you want something that does things for embarrassingly parallel programs. For really, really complicated parallel programs like a fast Fourier transform, this is not very useful. A fast Fourier transform has a huge amount of communication overhead if you're trying to do it on a parallel machine. This is not the framework that you'd want to do it in. Not every program can be done in this framework. There's a certain set of programs that can be done in this framework, and these are the embarrassingly parallel ones. Okay, so what is Spark then? So Spark is basically Hadoop. It's basically taking these ideas that are behind Hadoop, that we have this external program which is doing this orchestration, but it's also saving things to disk in between and doing all of these things for us, right? And it changes it by adding 2 features to it. It adds something called an RDD, which is, I think, a resilient distributed data set. It changes that, and I'll come to exactly what that is in a second. And what it does is that it actually, with the notion of that resilient data set, it actually keeps things in memory as well so that you can do things iteratively. In Hadoop, if you want to go back to the same data set, you have to pull it right back out of disk. In Spark, you don't. So it's an improvement to Hadoop, which makes things much, much faster. But the improvements don't stop there. So they've done a lot of good stuff over here. So that's the Spark core. What I just talked about is a Spark core part. And it talks to various things that are part of the Hadoop ecosystem. But on top of it, basically, they layered a machine learning library called MLlib, a graph library called GraphX, a streaming library, Spark Streaming, and a SQL library. And that SQL library is actually used to make the data frames. If you remember when we were talking about data frames in SQL long time back in the 2nd or 3rd week, we're showing you how similar those things are. And that's actually leveraged a lot in Spark. And then on top of the graph library and the machine learning library, there's a machine learning pipelines library. If you've been doing homework 4, you know why you want to do pipelines in machine learning. So they did 2 things. They took some of those really complicated MapReduce programs you have to write even to do a word count and made them simpler. So they created some abstractions. And on top of the abstractions, they wrote even better abstractions to do things like machine learning and so on and so forth. Okay. The basic structure of a Spark program looks something like this. There's a driver program which creates something called a Spark context, which is usually in code always abbreviated to SC. And you'll always be working with a Spark context. There's a cluster manager. And the cluster manager basically has things it executes at the back. That's it. That's the kind of structure. And if you want to see this in more detail, this is what it looks like. And this is an example of things running in Python. And so what it's doing is that you have this sort of like, what was the word I was calling it? The driver program up there. It has the Spark context. It's in Python. But basically, it talks to a little Java process over there. That Java process talks to Java processes at the back. And it does all the communication and all the sending the output of one function to the other. It takes care of it for you. That's the blue parts of this diagram, essentially. And then it opens up communication channels to the various Pythons, and those Pythons run your program. And you can use whatever is available on the Python on that machine to work with data out there. So you are sacrificing a bit of overhead, right? So instead of just saying f of g, where g is some function, and I run some function g on some data and doing f of that in a Python program, I'm doing f of g, I'm running g over there, and I'm doing f somewhere else, and I'm having to transfer data between them. So all of this only makes sense if you have a lot of data. If you have like a megabyte of data, you're probably better off doing it on that one machine, even using multiprocessing and so on and so forth. But if you have a lot of data, then the amount, and your computations are really long, then it's worth doing this because the network transfer is a fraction of the time of the whole thing. Otherwise, don't. So why is this better than Hadoop? It's in memory as opposed to disk. It can be in disk. There are different persistence levels, but a lot of these things just happen in memory. So it's kind of faster. It's really fast, actually, for large data. Look at, so this is a benchmark in 2014 that they sorted 100 terabyte of data in 23 minutes on 206 machines. The previous world record for that kind of sorting was set by on Hadoop and used 10 times the machines and 3 times the amount of time. So you get an idea for the kind of speed ups you can get. And it has interfaces in Python, Java, and Scala, and it's easier to use than the standard MapReduce framework. it still has the same advantages of being functional and running this kind of directed acyclic graph, basically, which you can reason about, independent of the exact parts of the program. So the key concept in Spark is this thing called the resilient distributed data set. And I'll just use, sort of like describe it with a quote from this paper. It's unlike existing storage abstractions for clusters which require data replication from machine to machine to machine to machine. We have our cross-validation data that needs to be humanly transferred or transferred by some kind of framework. Basically, RDDs, they offer an API which has based on coarse-grained transformations, and it lets them recover data very efficiently using lineage. And by lineage, I mean sort of like working this graph thing back and figuring out what needs to be run all over again. So there are two things about RDDs. Firstly, they're all read-only. You cannot write. This is the idea behind functional programming. I have an array coming in. It's a read-only array. I can't do anything to it. I will always produce something else from it. So that idea remains. It's read-only. The second thing is that it can be operated on in parallel. So it's like taking a list, and I'm taking this part of the list, putting it on one machine, that part on another machine, that part on another machine, that part on another machine, and I'm going to run in parallel on various elements of the list. Okay? Or in this case, various chunks of the list. Okay? So that's the second part. A list that is parallelized, or a file, or database storage, or something of that sort. So it's a fault-tolerant collection of elements, a listy kind of thing, which can be operated on in parallel. That's the basic idea you need to have. So in a data frame, for example, you can think of a data frame as an RDD, and you could think of the things in your list as the rows of the data frame. So here's row 0, that's one item. Row 1, row 2, row 3. And if I put this data frame, I might put the first 5 rows on one machine, the next 20 on the other, the next 10 on the third, depending upon the memory I have, and so on and so forth. So if I have a long list of numbers, I might take the first 1,000 and put them on one machine, the next 500 on the second. So that's the game I'm playing. And then I'm going to operate on these using the map function in parallel. Or rather, they are going to operate on it for me, and I'm going to tell it what to do in that map function. And for every chunk of that data, I'm going to output something new. I am never going to play with that chunk. That's the key thing. Okay. So you run a driver function that runs the user's, the main function, which is the wrapper, sort of your scikit-learn algorithm wrapper. And then it does all the parallel stuff on various RDDs in a cluster. So the operations that you can do are basically 3 types. Shuffle operations, as usual, are kind of done for you, as it's done in the Hadoop framework. But you do transformations, which are basically maps. You create a new data set from an existing one, and you create a new RDD. This is just functional programming. Here's a list, do something to the list, create a new list. Here's an RDD, do something to the RDD, create a new one. That's it. It's nothing new from writing these kind of programs on one machine. And actions basically take this and they collect it. They reduce things, and they create a number out of it. It might be a count, right? It might be a dictionary that it sends back of the word counts, and so on and so forth. It basically reduces the data. That's the non-parallel part. That's the part where you need to get things together. Those are the actions. The parallel part are the transformations, or the maps. So here is the word count example. This is it. It's 1, 2, 3. Okay, so it's maybe a little bit more than 3 lines of code of Python. It's really simple. The first thing is just setting up the data in normal Python. That's a normal Python list. And it has cat, elephant, rat, cat. Okay? The second line basically creates an RDD. It takes the Spark context SC, and it creates an RDD, which it takes this words list, and the number 3 out there, basically, is telling you, do it on 3 partitions. So what it's actually going to do is it's going to take this list, which is an admittedly useless little list to partition on 3 different machines, or 3 different threads, depending on whether it's running locally or not. Right? So it's what? It's 5 elements? Yeah. 1, 2, 3, 4, 5. So it may do some partition like this of the data. That's what that second line of code is doing. It's just partitioning this list into 3 parts. Then, by the way, this little bracket at the end of it is just a nice little piece of code to completely defeat Python's indentation, so that you can do your own indentation and make things look nice. There's nothing else to it, in case you're wondering what the brackets outside are. So then in the third line of code, what I'm doing is I'm saying, well, take the words RDD, which I have created by parallelizing this list, i.e., creating this list on multiple machines or multiple threads. Just take every element in this list and return a tuple W1. You know this. You've seen this. You've seen this word count before, so you know what's going on right here. Then On that, I'm going to reduce by key. I'm just going to add all the ones that I have for that W. So that's going to give me like W comma 7 or W comma 8 or W comma 9. And reduce by key does the combination of the combiner and reducer. It actually puts those two things together that Verena was talking about. And then finally, what collect does is it's this thing which is called an action. Collect just says, oh, I need all this data. Send it back to the main machine or the main thread. And that's it. So when you do that, it's going to give, this is the answer. You can actually, if you have Spark set up, you can do this. This is what it's going to give you at the end of it all. So that's WordCon. It's 3 or 4 lines of code. So, I mean, they've really simplified the API quite a bit. And this is what it kind of looks like, basically, in terms of the graph that they make for you. But here are your 3 things. Here are your 3 workers. There's a block of the list on one, the block of the list on the other, block of the list on the third. There's possibly a cache, and we'll come to the cache in a second, basically. And then we're combining all these things together and sending the answer to the driver. So in that, the up diagram came a little bit too small. But what I was trying to show you in that diagram is basically you have some RDD, which is this parallelized list, right? You start off words you started with, and you make some transformations on it. And you can make transformations on it, and make transformations on it, and make transformations on it, and then finally you collect things at the end. So that's the general paradigm in which you do this stuff. So here's the same example, basically, but it's using the constructor of an RDD called text file. And what text file does is it basically goes through a file and gives you a reline. So it's basically treating a file as a collection of lines. So instead of this list, you now have this list. So it's going to give you each line. And it's going to split this. So maybe this much goes on one machine, that goes on the other. And in general, if you don't give it an argument as to how many you want to do it, it'll try and figure out by itself how many machines to do it on, or how many threads to do it on, if you're running it locally. And then I'm basically doing the map, and I'm doing a reduce by key. And then finally, if I want to make it back, instead of collect, I want to save it in a file. That's also an action. I can just save it in a file. And the funny-looking URLs are basically if you're using Hadoop over there. But it should just be a regular file on your system that you can use over there instead. Okay, I'll skip over this because it's not completely relevant. So there's much more to this whole game. There's data frames, reading from data frames. You can read these. You can read on these kind of files, and you can create sort of have an interface to this which lets you actually query them in SQL instead, which kind of makes it easy to do a lot of selections. There's machine learning. There's streaming. And it coexists with other cluster applications. You don't have to get rid of your other cluster applications like your Hadoop apps and so on and so forth. You can run all of it on the same cluster. So these are some of the sort of like more practical advantages of the framework. Okay, so now I'm actually going to go and work through some examples. So all of this is not sort of like completely theoretical. And do that. So let me do that. No, that's not what I want to do. What do I want to do here? That's what I want to do. Is this readable? Maybe that's better. And I'll make these available after the lecture. So there's a lab recorded today which should come online some point tomorrow, which tells you how to install this stuff. The way we're sort of like recommending that you install this stuff is using what's called a virtual machine. Virtual machine is basically a piece of software that can run another operating system on your system. Now, if you're on a Mac, you don't necessarily need to do that. You could just use Homebrew if you know what Homebrew is about. But if you don't, you should use the virtual machine. So I'm not going to tell people what Homebrew is. But if you know what Homebrew is, it's as simple as this. What the virtual machine is going to do for you, and this is especially true of folks who are on Windows, Spark has a really, really, really hard time running on Windows. A lot of things don't work. What this does is that it installs a piece of software called VirtualBox, and it sets up VirtualBox with inside VirtualBox, it runs a Linux operating system, and on the Linux operating system, it runs Spark for you. With all the Anaconda, Python, and all that stuff set up, Richard, who's back in the audience there, he's done all the hard work of putting it together. So it's worth kind of using it. And I've also sort of like, I use this piece of software called FindSpark, which helps you find out exactly where your spark is. So this is how you start things off, basically. I'm importing FindSpark, initializing it, importing PySpark, and creating a Spark context. Everything starts with the Spark context. So let's run this. Actually, let me run that first piece of code. Okay, so I can't run multiple, so I need to stop mine. So let me just actually do that, because I was... Actually, you know what? Let's stop this. And let's restart the whole notebook. So we have a fresh start. Okay. Start all over again. And run that. Okay, so once this runs, it takes a little bit of time to run because it's actually spinning up Java and all of those things in the background for you, so it takes a little bit of time to finish. This is what the output on my terminal looks like, basically. It sort of shows you all these various things it's actually starting up. Basically, starting up a memory store with the default capacity of 273 megabytes and so on and so forth. A web server, yada, 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 blah, blah, whatever. You know, it's stuff you'd see on your terminal if you, with the IPython notebook was running. And SC is basically what's called a Spark context. So now here's your first example. And it's a really, really simple example. All I say is I take a list of 10 numbers, or 11 numbers. I think it's actually 1 through 10, yeah. So 11 numbers. I'm going to parallelize this list. So I'm going to actually split up this list. And since I'm running all of this in what's called a local context, I'm not actually sending it to different machines. I'm running it in just local threads on one machine. I'm going to split this list up into different parts. I'm going to map. So for each value out there, I'm going to get it squared. So for each list which is on a given thread, I'm going to take the square of that list and output that. So now I have these 3 different threads. All of them took a list in, produced a list of squares. And then there's a reducer which is running at the end. That is the sum, which is basically summing all these things together. And the syntax is very nice because what it does is that everything is a Spark context. All these functions basically return a Spark context. So all you have to do is that you can just chain them. You chain them one after the other after the other. It's kind of nice idiom by returning the same thing on which the functions are defined. And so I sum it, and I'll get a sum of the squares. Oh, what did I do? Yeah. Did I do that? Did I? Oh, no, here we are. Okay. Let's go back to that example of the cats and the rats and the elephants that we had. And it's a word list. And again, I'm going to parallelize it, and I'm going to put it on 4 different, rather largely on 4 different machines, rather expansively. So now here's one of the first important things to understand about Spark. That until you actually do collect, nothing is run. It just doesn't run anything. It claims that it's actually done this parallelization over there, but it's actually done absolutely nothing. It will only do it when you run an action. And you'll see why in a quick second. But so nothing happens. It's only when you do the collect that it actually runs. And you can actually see that in your program, where you can say, it says starting task 0, task 2, task 1, task 3, and then it says finish task 0, task 1, task 2, task 3. And all this thing did is basically, it just took that list and it collected it and gave the list back to me. Stupid program. Does absolutely nothing. There's no mapper. It's just a list. Well, give me the elements of the list. Okay? Okay. Something just marginally more interesting. I'm just going to pluralize these animals. Right? So make plural, take a word, and return the word plus s. Again, notice this function doesn't change any state. It takes something internal, returns something else outside. So if I do just normally make plural of cat, it's going to give me cats. So this is a transformation of RDDs. So what I'm going to do is over here is I'm just going to take this word, and I'm going to make a plural.rdd by just mapping it. And I can do things like first or take 2 and so on and so forth, and that'll give me different parts of this list. So here's make plural. And if I just take 1, it's going to give me the first one. That's cats. And if I collect, it's going to give me all the plurals. none of this is kind of unexpected, right? All it's doing is that it's applying a map to that list. So this RDD is this like list on steroids, if you like. And it's doing a map. It's taking everything in the list, and it's mapping it by adding an S onto the end. And unique collected. It's giving me this at the end. So, okay. And the words RDD, if you remember, was this it's kind of doing this on 4 different threads on the machine, which is entirely overkill. It's just for demonstration. Okay. Now we can do key value pairs. So our word pairs, for example, I just take the RDD and I map it to give me the pairs of these. And so that what it's going to give me is what you might expect that it's going to give me. It's going to take each one of those, and it's going to attach a 1 to it, right, and return to me the tuple. That's exactly what's happening over there. And so if I run that, this is my next little Spark program, which runs a mapper, and all the mapper does is that it creates a tuple with a 1 added to it, with the 1 put as the second element of the tuple, and it returns a list of those. And so right now, I actually just also included this output from my terminal to show that, look, there are 4 different Pythons running to do this thing. Okay, and now finally we can come to the famous word count example, which we showed you earlier, where you create the words RDD by parallelizing this. Again, you're running it on 4 threads. You're mapping it to get these word pairs. After that, you're going to reduce by the key, and then you're going to collect. And if you do this, you get the 2, 1, and 2. And reduce by key is the thing in Spark which tells the Spark runtime that basically do what Verena was saying, which is that if you can, run those combiners. And so it actually runs those combiners in the background on the individual partitions of the thing. So each one of these is an individual thread. And if you had A1 and A1, it just returns that. And if I had A1, A1, B1, B1, it returns A2, B2, and then A3, B3 over there, and then it combines those things together on the latter stages. And you can notice that these are like 3. The way it does it, the partitions, it's kind of entirely up to the framework to do it. And here are the partitions where it actually put all the A's on one and all the B's on the other. And over here, it had some kind of combination of things based on how the array was initially split up. Again, you can see you can use toDebug string, by the way, to see what the kind of graph of your program looks like. And so this is what the graph of this is. How much time do I have? 20. Okay. So very quickly, I think it's really important to understand what the cache thing is over here. So when I do this, remember I said that Spark is lazy. It actually never runs anything until you actually do an action, until you do a collect, or until you do a sum or a count or something, which tries to get you 1 number or a few numbers at the end. So here's again the same example. Until you do that words RDD.count, none of the other stuff actually runs in the background. It's just like it sort of saves it in a log, in a journal, if you like, and it says, okay, run these when the count thing is done. When the count thing is done, it runs those, basically. Okay. Now, if I was to call count again on the words RDD, it's going to run the entire program again, right from the beginning. And this is really critical to understand. It will run the entire program again on that second in input 15 and output 15, words RDD.count. The whole program runs again right from the start because of this laziness. And you might say that that's actually kind of a useless thing because I don't want the whole program to run again. I've already run it. What I would really like is a system by which things that were broken, things that didn't work, things that had to be saved to disk, only those parts get run again. That part of the graph, which I need to get run again, gets run. So to do that, what I do is I use this thing called cache. I say words RDD.cache. And that itself is also lazy. It does nothing for you. It just says, oh, the fellow told me to cache it. And I say, okay, you're going to cache it. Okay, so I run that. So let's just run these. Now, when I run it the next time, when I do it in that input, what is it, input 17, when I run the count again, this time it actually caches the words RDD in memory. So it doesn't actually recreate this words RDD from the words list. It caches it in memory for me. And now if I run words.count the next time, this parallelized business is not run. So in the input 18, this thing happens right off the bat. So obviously this is not a very useful example because it doesn't do anything that's kind of particularly useful because you're just caching the first step. But here's a somewhat more useful example where I have a list of birds, heron and owl, and the words list were all mammals, so I put those together. And I have a little dictionary, which I create, and I can look at it. Animal dict. And it's telling me what these things are. Okay, so let's do this in Spark. I'm going to take this animal list, basically, which I've constructed by combining the mammals and the birds over here. And I'm going to cache it right at the beginning over there. So when I do the mammal count step, it runs the whole chain, right? Because the cache doesn't do anything for me at that point. It just tells it, cache it. So it creates the parallelization, gives it an order to cache it. And then finally, when I do that first filter, where I'm trying to filter basically by anything that's a mammal and counting how many mammals I have, it runs the whole chain, but it causes the cache to be created for me. Now, the second time when I do the bird thing, only the filter is carried out. It doesn't go all the way to the top. Otherwise, in other words, what it's doing is that it's saying that I have some kind of graph over here of the execution. And if I put in a cache thing at this step, and this went off in two different directions. That's what's happening here. I'm looking for mammals here and birds out here. It's run this part. It hasn't run this. But because I told it to cache it, the next time it comes around, it just does this. Just that branch of it. Because it knows exactly where you are in the graph. So it's kind of really smart that way. And so you can use these cache things to speed things up a lot. Okay, so here's an example of, so that's what this one is doing. So that bird count is running off the cache, whereas the animal count ran by actually running the entire program. So here's an example. I'm just going to actually build it up in a step-by-step fashion. This is basically, I'm taking a bunch of stop words, because I don't want the stop words to be in my frequency histograms. And I'm taking the entire text of Julius Caesar. I'm taking the entire text of Julius Caesar, and in the next line, instead of using map, I'm using flat map. And what flat map does is the following. Remember when I said when you're reading a sc.txt file, what it does is that it treats it as a list of lines, and it'll put some lines on some machine and some lines on the other machine. When you do a flat map, it does actually a map and a reduce together for you inside it. What it does is it takes each one of these lines and splits it up into the words. And then it says, well, now I have a list of lists, right? I have a list of the words in this and this and this. Flatten that whole thing out and give me a list of words. So it does this mapper and reducer combined for you. It takes care of actually scheduling it and everything for you. And so you do that and you get a flat map. So basically what it's saying is that take the split of the line. And what take is just basically showing you the first 20. I just want to see the first 20 because I don't want to see the whole Julius Caesar stuff. So now it's basically a huge list. And instead of take, I could have done, I think I can do, for example, count to see how many I had. Oh, I haven't run it. It should not be smart. And that's 21,000 words in Julius Caesar. Now, when I do this again, of course, it's going to do the entire thing again because I haven't done any caching. Just remember that. So it's now doing the entire thing again. So now what am I doing? I've used the line.split in the flat map, so I've got all the words. And because it's flat map, it's not just a list of words, but it's just a list of words. I'm taking that list of words, and I'm going to lowercase it in my next step. So that's my next transformation. So my first transformation was the lines of the file to the words in the file to the lowercase words in the file. And then I'm going to take 20, which is my reducer, my overall reducer at the end, my quote-unquote action, and it's going to show me the lowercase words in Julius Caesar. And then I do the next thing. I'm going to do a filter. And the filter is basically give me the words that are not in the stop words. So get rid of the A's and the ands and the is and the does and that kind of stuff. And take 20 again. Boom. So you can see, for example, that like off and by and the went away in this thing of words over here. All right, so let me do the next thing, which is your famous word count example, and get the tuples back and take 20 to see what that output gives me. And it gives you what you might expect, this kind of rather strange way of emitting tuples with these ones, essentially. And then I'm going to do the reduce by key, which is basically doing the entire reducer and combiner together for me. And it's giving me a bunch of counts. Like muffling came in 1, sleep came in 6, And pardon came 5 times in Julius Caesar, not surprisingly. And then I'm going to take the ordered, the top 20 ordered ones, and it's ordered by the second element, but the negative of the second element. So what I'm basically trying to do is to get a descending sort, essentially, from it. So that's a descending sort. And so that gives me that Brutus and Cassius and thou come quite often in Julius Caesar, apparently. And now I can go and make a little plot of these. And there you go. Here's a little bar chart, which tells you the... And look at the code to make this bar chart. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of Python. Really simple. Okay, suppose you want to do a whole bunch of Shakespeare plays. Just use text file with a whole bunch of Shakespeare plays, with a glob like this, which is saying start.txt. I have a bunch of Shakespeare plays in there, basically. And it's exactly the same game you play. And I say at least 4 partitions when you do this, because I want to run it on at least 4 threads. Okay, this does not like me. Oh, you think it's my phone? Could be my phone. Did something happen on my phone? Electromagnetic activity? No. Take it off. Okay. And so I do that, and I'm running exactly the same piece of code. And boom. And this time it's going to take a little bit longer because there are about 12 or 13 or 14 plays in there that I have. And it's running it on at least 4 of these threads. It's going to do this on for each one of the... It's going to take all those plays, combine them together into one huge, big, honking list of words, and then do this frequency analysis on the words. And there you go. Apparently, Shakespeare really liked thou, or thy, or good. Not so surprising. Nothing that exciting. Okay. Very quickly, you can convert pandas, Spark data frames to pandas and pandas data frames to Spark, but it must fit inside memory for you to do this. One critical difference, if you remember in pandas data frames, you could always create new columns. Why can't you create new columns in a data frame in Spark? Anyone? Go ahead. Because it's read-only, exactly. You've come up with this beautiful paradigm which works because everything is read-only and you can reason based on this graph and everything. If you start supporting everything that is there in pandas data frames, you've just broken your paradigm. So you don't want to do that. So remember, Spark data frames are read-only. But otherwise, everything else works. I mean, this is the kind of code you would write to do maps and reduce by keys to do a group by and average in Spark. But so the data frame syntax actually simplifies a lot of things for you. And almost all the commands that work in pandas actually work in Spark. And this is what it does under the hood for you, essentially. So one of the beauties of Spark is not only did they actually do all the MapReduce stuff, the basic stuff, but then they composed it very nicely into a good API, which you can use. So here, for example, is those heights and weights data set we've been using in the labs. I can read it. And from PySpark.SQL, I import a SQL context, I create a SQL context, and I create a data frame from it, and here's your Spark data frame. And I can show, instead of head, I have show, and those are 5 lines of the data frame with this rather nice-looking ASCII art rendering of the data frame, which I don't know, I think I may actually like it better than the usual rendering. And then you can do some stuff, like you can look at sparkdf.gender, and that's actually going to give you the gender. It's basically gives you this kind of columnar notion that regular pandas gives you. Here the map I'm doing in temp basically is I'm basically just asking it for the gender. So it's a map in which I'm saying go to each row. It's again the same idea now. It's just the same idea as this of the file. It's basically saying here's my data frame. Go to each data frame. Go to each row, because that's the element of my quote-unquote listiness of that data frame. That's how I've split it up. And in each one of those rows, give me the thing which was in the gender slot. That's what that map is doing. And then it's saying combine everything which was in the gender slot. So this, combine those 5 things into a new list. And that's what you see out there, male, because in this particular data set, 25,000 males at the top and 25,000 at the bottom. Okay, so now that we've done this, let's go to the logistic regression we did in the lab, right, on this data set. And we'll finish with that. So From the classification module, you import logistic regression with LBFGS, which is a minimization algorithm. And we import something called a label point. And label point is really the critical thing here, because that's how it represents the kind of, sort of like design matrix that you've seen that scikit-learn uses. And it's a slightly different way you do things. And you can see how it is in this particular map over here. So I take the data frame. Remember, when I do this map in the data frame, it's doing data frames by rows. So it's taking each row. And that's why I've said lambda row over there. So this is in input 38. And I just returned basically a labeled point, which is the Spark notion of an array in this case, with the first element as a response I want. So the response I want is that I want it to be 1 for all the males. So I'm going to say that the row's gender is male. So it's going to be a 1 there. It's going to be a true there, really, or a 1 there, and a false otherwise. And then I'm going to actually return the features matrix after that, which is the row dot height and row dot weight. So it's actually only giving you those two numbers, right? So what it's doing is it's giving you these two numbers over here. It's taking this. So basically, it's going to create a label point with this response and these features over here. And you can see what it looks like, because they sort of, when I do a take 5, they're very nicely printed out for you, and they say it's a label point with response 1 and that part of the feature matrix. You could also do it in a slightly different way, which I show you in 39, which is kind of, using the Python array indexing notation. And then, no, I don't think you read the data. Yeah. Notice what it does is that in the second part, if I just do the features, it actually writes over here. This label point has two properties. The label itself is the property with the value 1. Basically, that's the response. And the features is basically the features. And it makes it into what's called a dense vector. And now I can do my random split my data into a train and a test, and I immediately cache it. And the reason I immediately cache it is when I do something else in the future, what I'm going to do? I'm going to actually work on the training set. I'm going to fit the training set, right? And then I'm going to want to predict on the test set. But if I don't cache the test set, remember, Spark is lazy. So what's going to happen? It's not only is it going to create a new test set, you're absolutely right, but it's going to run every piece of code from that point back all the way down, which I don't want to do. I don't want it to repredict stuff. So kind of useless if I did that. So that's why I need to sort of cache it over here. OK, so I run this. And then this is just the type that train and test are. And then I do the model over here. And this is very similar, and it's going to take some time because it's running it on these multiple threads, and it's probably more useful in an even bigger case. But this is running the logistic regression, and it's .train, just like your scikit-learn's logistic regression .fit, right, on the training set. That's it. It's going to take the training set, it's going to fit it, it's going to tell you what the model weights are, and here are your coefficients. Remember, it's a two-dimensional problem. And then I'm going to predict. And the way I'm going to predict over here is I'm just basically going to say, take the test set, map everything in the test set by going line by line in the test set, get the label. Let me write out the label because that's the actual value. And let me do a predict, just like scikit-learn predict. Basically, model.predict on the features. And I'm going to convert the prediction to a floating point because it tries to, when it actually predicts, it predicts ones or zeros as integers. And I want it to look like this. So for example, here you are. Here's the first two results. I can actually probably take more, all of which are extremely male. It predicts them entirely right. And I can actually do the test accuracy because I got these results now. And the results is also an RDD, which I'm getting out of there because it's a result of a map. And I take this particular RDD, and what I'm going to do essentially is I'm going to do a filter. And I'm going to say, well, each of these results is a tuple. Give me only those tuples where the two elements are equal. And count those. And then divide it by the total number I have. So it's actually, so this thing is basically, it's taking a filter over there, and it's taking another accumulator over there, and it's dividing the two by each other. So it's dividing two actions by each other and giving me a test accuracy. And you can see, you might remember this from the lab, that it's about 92% on this set. And they even have like something like a binary classification matrix. I can take the results and just pass it as a classification matrix. And for example, I can get the area under the ROC curve in one line. So in some places, the sort of like interface is even nicer than scikit-learn's interface to do machine learning. And finally, I can actually save this model down. And it's saved in a particular formula, a particular format called Parquet, which I'll let you read about and not bore you with. So I'm going to actually remove what I have here. And then I can basically save this model and use it for later. And when I do this, it basically saves it in a CD project. And here it saves it in mylogistic.model, and it's a particular format in which the data and the metadata and everything of the model are saved. And now to just finish things off, you basically stop things. And you're done. And so using this idea of MapReduce, not only have we now seen how to do simple things like word counts and so on and so forth, and the word counts are really good because they help you understand what's going on, but you can see how these ideas are now sort of like taken into the machine learning part, where you're taking things and you're making predictions of them. But again, each time, remember, the critical thing is you take an input array, you do something with it, and you produce an output array. And this is the thing. And no state is harmed in this process. And this is the critical thing that lets you have an external thing come in and schedule everything for you. And that's the whole reason. So finally, why do all this? We have lots of data. Why do all this? We have a lot of compute. Why do all of this? Our machines are going to die. Our processes are going to die all the time. So you do all this, do it in this kind of functional fashion so that other people can do a lot of the work for you, i.e. the framework. And so do all of this, put this all together so you can solve really big problems. Thanks.